Okay, that's my crazy class. I said, all right, we're going. Silence. And they're all nuts. We're live. Okay, so here we go. Gonna do the next one. Boom. All right. So the reason I'm just gonna keep talking until everyone settles down. Of course. Um, I'll get that. Um, so I start with this little cutout from the book, and I was thinking about not telling the story online, but I guess I will. I think I said the story to at least one, if not all, the classes about this chapter. And a year ago to this day, fully admit, this is a brand new class for Truesdale and I last year. Struggled to teach. Could have very easily just given us a history class to teach. Now I don't even have a history degree, and it would have been the same amount of work. Just trying to get ahead of the students, trying to figure out what the heck is going on. Fully admitted that last year, but then found it really interesting. A year ago to this day, or right around a year ago to this day, right in this chapter of doing graphs and networking, Truesdale goes to a Notre Dame game. True story, unless she's lying to me. Um, Over the weekend, she comes to me on Monday. You're not going to believe what happened to me. I went to a Notre Dame game with my husband, sitting down in the stands, and of course, you know, people you're around, you start talking to, and the guy that I was talking to, this is what he does for a living. He's a networker. He's, he does this kind of thing where you get efficiency and well, specifically what he did, I refreshed my memory and talked to her yesterday. What did this guy actually do? And he was on a college campus, and his current job was to get wireless internet that's accessible anywhere on campus, inside and out. And currently what he was trying to do is getting the outside routers, which he was attaching to light posts outside, and his job was to do it the most efficiently, using the least amount of routers, so that the network would still be good enough to come back to the tech office so that they could get that wireless um, internet out to everybody. And that's was his job. The efficiency, less routers, less costs, and still the most strength in the signal to make that happen. The guy flew in his own personal jet to that game. So just take a minute to think about that. This guy that does this for a living, efficiency and networking, big time money man. So with that being said, this paragraph out of the book really coincides with that. Business managers and administrators often carefully analyze the efficiency of a network as it can affect the bottom line. That's what this guy's job was. Less costs, but the most powerful network that still worked efficiently. For example, you might want to minimize the length of a wire used in a computer network or the mileage that delivery vans must travel. One thing I told you about this whole chapter as well, UPS truck driver. How can I most efficiently visit all of these points, all these drop-off things? All right, so what we're going to go into today is creating a graph of making it weighted. And what the weight of that graph, as I point to the sentences I'm in class, those weights are cost from going from one point to another, or the time it takes, which time is money, or the distance it takes for like the driver. All right, so from this information, this is what you can first write. Of course, he did not write any of what's in that sentence. Isn't this great animation? All right, so a weighted graph. Each edge has a number or a weight put on it or associated. May represent time, cost, distance, pulled right out of this paragraph. Okay, so again, I just wanted to give the book props, I guess, as far as where does this pertain to in the real world? Not that I'm saying you're going to go out and do this, but maybe you make a career change and you'll see that this is something that would happen. Of course, the second one is assigned such as they are relevant to the problem, of course. This is important for you to understand that it's not what you have to do. The length of the edge does not have to be proportional to the weight. So the length of the edge does not have to be proportional to the weight. And what I have is a drawing that I put ahead of time here. All right. This is what this means. Pretend from point A to point B is 7 miles. I think that's what I put there as I move around. Yep. And then point B to point C is 6 miles, and I decide to put that graph as such. Then I read from point A to point C is 3 miles. Well, obviously the longest line here is from A to C. Doesn't matter. In fact, it would be really hard, not saying impossible, but really hard to make these lines proportional and have the drawing actually fit. It's not your job. Your job is to put the weights on the lines, and that's all that matters, not the length. Okay, and I'll give you a minute to write that down. Okay, next. All right. So I'm going to try to do this. Last hour I could not write on a PowerPoint, which is a very legal thing to do, to be able to write my own writing. That's what happened. It just, everything went haywire again. I honestly feel there's someone in the tech office that's connected to my computer. You know, Samuel's having a good day. Let's start screwing around with them. Blah, 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 and then my computer just starts going crazy. Control my desktop. I feel it. What do you think? Are you even listening anymore? Sick of my stories, aren't you? All right, so it takes good old Mr. Samuelus. You don't have to put good old. You could put ugly, disgusting if you want. 30 minutes to get to work from home. 180 isn't all screwed up. I don't think you really need that for the problem. 20 minutes to get to the kids to karate from home. And 25 minutes to get to bowling from karate, which is actually my life. That's what I do. All right, so I'm going to try this. I'm going to try it. Pen. Okay, so then this is real simplistic. I got to be real careful how I write on the screen. Otherwise, everything will get jacked up. So let's call that home. So I'm writing like my 7-year-old would write. Actually, that's an insult to my 7-year-old. She writes better than this. But it's the slippery screen, like I'm writing on ice. Where am I going? Oh, work. Good old work. And then you put a 30 on that. Now it's a weighted graph. It's the only thing we've added. This is Mickey Mouse. And then 20 minutes, kids to karate from home. So home to karate. Notice I put those as the same. Length. But I put a 20 on that, and that's all that matters. And then 25 minutes from bowling to karate. So that's what I had. I drop the kids off at karate with the wife. Then I go off to bowl. The wife takes the kids home. 25. Now that's a much different graph than I had first hour. It doesn't matter. You can put home over here. You can put home to the upper right. You know, it doesn't matter. Not all graphs have to look the same. The connections must be the same, though. So there it is. Just a weighted graph, real Mickey Mouse example. I know. How about it? Shocking. Oh, I think I'm still stuck in pen mode. Okay, there we go. Boom. Don't worry about the highlighting. I'll have that figured out. So I'll give you a chance to write this down. And hold off on the chart for a second. Amtrak travels between 6 cities. The distances between each are shown in the table below. I'll hold off on that table before you write down, if you want your notes to be nice. Draw a weighted graph to represent the system. And then the reason for letter B, find 2 different routes between Nashville and Indianapolis, which could be called subgraphs, is because when I reveal the chart, or when the computer lets me do it, there is no direct connection from Indy to Nashville. So understand how the chart is read. And I guess I will blabber as you're writing this down for those that take notes. I see a lot of people not doing that. Can't wait for an open note quiz. I don't have any notes. That's your fault. Why do I have the bottom left highlighted? Because there's redundancies in this chart. I know it's different to go from Detroit to Chicago than it is to go from Chicago to Detroit, but isn't the distance the same? It's the same track. So when we do our graph, which that chicken scratch is on the bottom was part of my disaster of first hour. I could look at the writing, and then all of a sudden the computer started betraying me. Someone in the tech office pressing buttons. Let's mess around with Mr. Samuelis. Anyway, there's not two connections there. You don't draw a line from Detroit to Chicago, and then you don't draw another line from Chicago back to Detroit. So really, when you're making your subgraph, you only have to look at the bottom left or the top right, because they're the same. From Columbus to Detroit, it's 204. From Detroit to Columbus, it's 204. So when we do our graph, we're only worrying about those. So I'll give you a second to write that down if you want good notes. Look at this stuff. Is it going? Yes. All right, so we constructed this graph, I think. Oh, I forgot I can't do that pen. This graph in class. Okay, then you can look at the one. It's coming, I think. Working lightning fast. Is it showing up there? Okay. So ours on the board looks better than this. This is similar to what we did second hour. So making the connections one at a time. I did Chicago first, direct lines to all the cities, and then I only worried about the bottom left because I don't care about the top half because we're not drawing two lines, one from Chicago to Detroit and one from Detroit to Chicago. So I'm worried about what I'm saying online. Okay, so on the next thing, you construct this graph. Not all the graphs have to look exactly the same. Now we're going to look at from Nashville to Indy. And the whole point is this, and you should be listening to me. It's hard to see in the chart, but now it's easy to see on this graph a couple different ways I can get from Nashville to Indy. And I do have this come up, so I am going to stay here. I'm going to risk it that I'm able to write on this and show highlighting. And I'm going to try to emulate what I did in the other class. So here's from Nashville to Indy. I think you could see that one direct way is Nashville to St. Louis, and then St. Louis to Indy. Do you see that? Can you see that in my highlighting right there? Correct? Okay, and I could go up to the board up there and show it as well. And that would be one way to do it. But then, seeing that on the graph, is that as efficient as maybe a different way? Well, we'll check, because what we need to do is add up those distances. So from Nashville to St. Louis is 584. St. Louis to Indy is 354. Those two added together, something like 930 something, right? So 930 some miles. 930 what? 938. Or I could change my highlighting. Is there a different way and more efficient way? Maybe I can change my highlighting. This is going to be easy. And the answer to that is yes. What if I went Nashville to Chicago, shaky, shaky, and then Chicago to Indy? That would only be 515 plus 110, and you're getting the same thing done. And now what I want you to understand as I have this appear up on the slide, boom, those two, which you might not be able to see up there, but maybe at home you can, is that's only 625 miles. And then I want you to think about the whole spirit of this this section. It's about finding connections that are more efficient. And of course, this is a Mickey Mouse example. The point of the graph is being able to see the connections. Maybe not so obvious in the chart, but in a graph it is. And then maximizing those options. Everyone okay? Get it? Move on. No, this may not be working out as well having cutouts from the other class, but it's what I'm stuck with. With what we have here is technology that's not working out so great. Subgraph. Subgraph is a set of vertices and edges chosen from the original graph. And actually, in this one, I will do all the questions on the board and then just have it, show up for those at home and not reference it anymore. But a redundant connection. Now, this kind of leads into tomorrow, another efficiency thing. We could call it like the Truesdale guy that she saw at the Notre Dame game. Redundant connections not necessarily needed, so I could use less routers. That's kind of the idea there. If an edge can be removed but still maintain a connection between all vertices, Routers. If there is a circuit, then there has to be a redundant connection. So I'm going to try this again as you're writing this down. So far the pen hasn't betrayed me like it did first hour. If I have A to B to C, this is actually a circuit, correct? Right? So there is a redundant connection, meaning I can get rid of maybe this edge, and all the vertices are still connected, so I don't need that edge to keep the connection of all the critical points. So this is what removing a redundant connection looks like in the most simplistic way I can show it. And I hope that makes sense for you if you wanted to write that down. So this was here. I could get rid of this one, and I would still have the vertices connected. Of course, I lost my vertex. Don't know why. All right. So that would be another way to remove a redundant connection in the most simplistic form. I'm going to erase this, and then actually the last set of notes are another chart. Okay, and it's very similar to the one we just had, but much smaller cities. So I'm going to go to my board, ask for a volunteer to, when I'm on the board, what are those mileages, make another graph, and then what I'm going to do is make 2 different subgraphs that removes the redundant connections, that keeps the cities connected, but we remove redundancies in it. And we'll talk about that on the board, and then I'll have to reiterate it on the computer where the class doesn't really have to listen to that. Then you don't have to listen to the second part. But, all right, so we did this in class. Draw a weighted graph to represent the commuter airline network. And we went a step at a time and came up with this drawing. Okay, and it's very similar to what second hour had. So, boom, there it is. Right? Should look better when you look at this on a hard piece of paper. Now what we're going to do is remove the redundant edges. So what that means is no circuits should be in there anymore, and all the cities are still connected. So we're going to do that in class, and I'll be back to the video. Okay, so we went ahead and did 2 subgraphs that removed redundant edges, which means there are no circuits left. So one of them was... actually, we didn't have this one, I think. Nope, that's not the one we did in class. We did something a little different. Yep. Okay, but that is one. Notice the cities are still connected, but there are no circuits. So I could hit all the hubs without any problem. And then here's just another one. Not a big deal. We did 2 different ones. Here's another subgraph from the graph given. That's not even one. I have 2 different ones in the notes. So you guys, period 3, have the, you have 4 different subgraphs to look at that all did the same thing. 1290. Oh, that's bad. Yeah, this one's so we have one in class. We had a subgraph that is weight of 1030. So we'll talk about that more tomorrow, trying to get the most efficient subgraph possible. Oh no, I'm sorry. One of those is so 3. Whatever. Sorry, blabber.